Hi, my name is Lukasz and I'm the part of NeuroBeat team. I was a main programmer, so I want to introduce you our implementation part of NeuroBeat application that we designed for Brain.io hackathon. And thanks Jitek and Christopher for organizing this hackathon. And now I want to show you a part of our mind map we start with before starting our implementation. Here we've got basically a part of Lucid Chart application. So let me start the presentation. So we started from, of course, collecting real-time data from Unicorn, and after that we need to define a streaming protocol. So we basically because of the short time of hackathon, we tried to use the Python first, but we switched to the Touch Designer application, which is development environment for designing real-time stuff in it. So our goal was to basically stream the data from the Unicorn as fast as possible to Touch Designer. For that, we basically used the LSO streaming protocol that Digitech and Unicorn put on their GitHub. So we compiled the code, the little application that streams data. We basically, after that, we did a little program in Python to redirect the data to the Touch Designer. So in Touch Designer, we started from the filtering section. So we've got a bandpass filter, of course, some notch, and our pre-processing is based on the band analysis and really sharp bandpass filter. Not so big order, but still a little bit sharper than normal filters. So we started from maintaining this filtering part, and after that we started to design our application for training. And here we come to the part of here we go to the part of the application for the training, where we record the data and we do some baselines with it. We also have here, as you can see, for the prototyping, a white noise baseline, but we didn't basically use it in that application right now. But we use open and close eyes, and basically we create a score table for frequency and amplitude. And after that we end user calibration, so we know the minimum and maximum of the desired frequency from the user, and we are starting our session. Basically, we want to produce the binaural beats, which are basically the difference between two tones. So for the first part, we measure the user main frequency band by selecting the amplitudes and of the filtering part and measuring the median of it. And after that we update the user to be as close as possible to desired frequency. So for example, when user is in beta state, we want to take him to the alpha by step reducing the difference between two tones on binaural beats. So that's basically a part of just describing how the workflow goes. And here we got in Touch Designer application. And also this is this little upstreaming layer up from the Unicorn, so you can stream, you can design your stream name, and after that you can take the data. So coming back to the touch designer, we started basically from the part here. So we by using OSC protocol, we get the data from the unicorn, and we also check for the correct packets. So if some packet is not getting right or is corrupted, we just removing it by this validation validation parameter, which is coming from the unicorn. After that, we compute the trial of 4 seconds, and this is only to basically make some measurements and to make spectrum analysis, from which we can derive activity map of some of the states. But this is just for just like prototyping, and was not used in final application, but we also designed that part. As for calibration, we've got 2 modules. So it's like one is a close eyes, and we initialize it. After that, we after initialization, we record the baseline, so we can define how much time it should spend for recording one baseline, and after that we've got the spectrum of our baseline, and also we've got the minimum and maximum values of alpha band and also the bandpass. So we can adjust from these parameters dynamically our thresholds for the real-time application training. And so the same thing happens with OpenEyes baseline, and here we've got a part of real-time processing. So here we get the data, which is coming raw. Is just for now we taking the part of 4 seconds in the front, and after that we basically just take a part of it to be as fast as possible for filtering part. So so this goes here in this bad container, and here we got some basic validation. So like here we can see we already trimmed the data. We attached the notch filter. Also we trim it in front. We push the high pass, another band pass, and the band pass with notch. And after that we've got basically respawn the spectrum, which we use only like a preview for developing, and we've got also this little time window with 154 samples for real-time analysis. And here we've got our filtering section. So we have our components classes, which we can easily redefine for more adjustments, and this is just also defining a filter for a specified frequency with specified parameters, and basically and specified bandwidth, and after that we taking the maximum and the minimum of that samples, analyze it max and minimum. And after that we end with something like you can see here. So the left part here, we can see here, for example, respawn of the alpha part of filtering, and we can see now is the blue one is like the most attractive one of this part. Is basically the part of alpha filtering. So we can see here is like around 8, and here is around 12. So we can see this, which is the broadband alpha, is just with kind of fastest alpha active mostly. So when we want to let me recheck this like this. So when we want to basically check that we normalize the data, and now we can see which one of this filtering section is close to the desired state. So 5 is like the fast alpha, around 12 hertz, so we want to go back to the 8, so we can define user to set his binaural beats to come from 12 to 8, or even lower if we want to design this like this section. And after that we got a logic which is checking like this between 8 and 12 hertz, and is returning the frequency we are standing on in that bandwidth. So after correction with the beta states which come here, we can define if user is not in high beta state, so beta is lower than alpha, we can adjust the move a little by little. This goes to the binaural frequency generator, and we've got two oscillators which are tuned by base frequency and target difference. So target difference is the result of the real-time processing part. One is set to left speaker or headphone, more headphone, and another one to the right. And after we turn it on, we can hear that sound is getting vibrated, and when changed and you keep focus, you can notice that the changes are pretty much respond for what you achieve to do. So when you're trying to go from 12 to 8 hertz, you can find out the regular connotation about that. So that's basically all for the NeuroBeat implementation. We hope you like it. Thank you very much again. We are very happy we could participate and win the first place in our category. I hope to see you in the next ones. Bye.